Okay, hello, this is Dr. Hanaa Assil, and this is about trends in the periodic table. This is for AS Chemistry at Excel, but it could be for any topic about trends in ionization energy. How does ionization energy change along a period or down a group? So let's take a look at, first of all, what is ionization energy? Ionization energy is the amount of energy required to remove the most loosely bound electron to form a positive ion. So, if we have an atom and we're trying to remove an electron, pull away an electron from the atom, the amount of energy needed for that is called ionization energy. And notice that we could be removing an electron from a metal or from a non-metal. In both cases, it is called ionization energy. So, of course, I need to give it energy to remove the electron. So, ionization energy is always endothermic. Okay, we could have first ionization energy, second ionization energy, and so on. So, first ionization energy is the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ion. So, this is the definition for first ionization energy. What does that mean? I have, first of all, I am removing the electrons from gaseous atoms. So the atom must be in the form of a gas. Now, what am I doing? First ionization energy, that means I'm removing the outermost electron from the atoms to form a plus 1 ion. And the amount of energy that is denoted for first ionization energy is actually the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms. So I have 1 mole of gaseous atoms in for a certain atom. We remove the electrons in this 1 mole of gaseous atoms. This is called the first ionization energy. And of course, if I remove 1 electron from atoms, they become plus 1 ion. Okay, so if I want to remove a second electron from this atom, so I already removed 1 electron, so I formed a plus 1 ion. If I try to remove a second electron, now this is called a second ionization energy. So the second ionization energy is the energy required to remove 1 electron from each atom in 1 mole of gaseous plus 1 ions to form 1 mole of gaseous plus 2 ions. So in this case, I'm starting with something that is plus 1. I'm going to remove 1 electron and turn it into a plus 2 ion. This is called the second ionization energy. And then you can imagine what would be the third ionization energy. Third ionization energy would be removing the electron from the 2 plus ion in order to form a 3 plus, and so on. So these are called successive ionization energies. So if we say define the term first ionization energy, how did we define the first ionization energy? It is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ions. Are we okay with all of this? Okay, so another question says, which of the following equations represent, that is second ionization energy. So which of these represents second ionization energy? Yes, that's the first choice that you have here. The second ionization energy, all of them, we're talking about gaseous state, so all of them have to be in the gaseous state. And then second means I'm starting with a plus 1, I'm removing 1 electron to form a plus 2. Okay? So what is the sequence of orbitals from which electrons are removed in the first 4 ionizations of boron? So we look at boron. What is boron? Boron from the periodic table has atomic number 5. That means we're distributing 5 electrons, and you should know how to distribute 5 electrons. We put 2 into the 1s, 2 into the 2s, and I'm left with 1. It goes into the 2p. Then he's saying, okay, first ionization would remove which electron? Of course, we start with the outermost electron. So the first ionization will remove the electron that is in the 2p. That's the outermost electron. And then the second ionization will go into the 2s and remove one of its electrons. And then the third ionization would remove the second electron that is in the 2s. I've removed all of this. I go into the 1s and remove the electrons one by one. So that means that my answer is C. Can you see that? Okay. If we're talking about the second ionization energy, for any element, the second ionization energy is always greater than the first. So if I have magnesium, for example, the first ionization energy will remove one of the electrons in its outermost shell to form a +1 ion. Now, what about the second ionization energy? Well, the second ionization energy will remove an electron from the +1 ion that has already lost one of its electrons. So that means that I have less electrons being attracted by the positively charged nucleus. So you have what we call increased nuclear charge. The electrons, or that energy level, is pulled more strongly or attracted more strongly to the nucleus, and therefore more energy will be needed to remove that second electron. So for any element, the second ionization energy is always greater. Once I have removed one of the electrons, then the rest of the electrons is pulled more strongly, more strong attraction forces to the nucleus, and therefore more energy is needed to remove it. So if we say sodium and we look at the successive ionization energies of sodium, you'll find that, okay, we need a certain amount of energy to remove that first outermost electron. Now, let's say the first ionization energy is +496. Of course, we said all ionization energies are endothermic, so they all have a positive charge. Okay, now if I try to take away the second electron, well, the first electron is removed from the outermost shell. So I have a weak attraction force between that outermost electron and the nucleus. So the first ionization energy is low. But as I go into the second ionization energy, the second ionization energy is going into an inner shell, which is more strongly attracted to the nucleus. So you see a huge jump in the ionization energy from the first to the second, because the first removed the outermost electron, the third energy level. Now I'm going into the second energy level, an energy level that is closer to the nucleus. So there is a huge jump in the second ionization energy. And then after that, I'm going to remove all the electrons in the second energy level. So my third, fourth, fifth, sixth, until the 9th ionization energy, I remove all the electrons in the second energy level. Now I need to go into the first energy level, which is closer to the nucleus, stronger attraction force with the nucleus. So there is another huge jump for from the 9th to the 10th, because I'm going into the 1s, or the innermost shell, which is closer to the nucleus. So if we draw a graph of ionization energies, the successive ionization energies of sodium. So we said sodium is 1s2, and then 2s2 to p6, and then 3s1. So the first ionization energy is removing the 3s1, the one in the third shell. So that is low. So the first ionization energy is low. Number of electrons removed is 1. That's the first ionization energy. That is low. And then we said there is a huge jump from the first to the second, because I removed the first from the third energy level. Now I'm going into the second. That's closer to the nucleus, stronger attraction force with the positive nucleus, so less easily removed. So I have a huge jump from the first to the second. And then a gradual increase from the second to the ninth. So I'm removing 1 electron successively from the 2p and then from the 2s. And then I need to go into the 1s to remove that innermost electron. There is a huge jump from 9th to 10th ionization energy. So, ionization energy depends on what? Well, it depends on several factors. It depends on the atomic radius. So, of course, if the electron I'm removing is further away from the nucleus, then there is less attraction forces between that electron and the nucleus, so it is more easily removed. So I will need less energy. But if the atom has a small radius, or the radius is becoming smaller, then there will be a greater attraction force to the positive nucleus. It will be more difficult to remove the electron, and therefore I will need more energy, higher ionization energy. So that's with respect to atomic radius. Now, it also depends on nuclear charge. How many positive protons in the nucleus are attracting the electron? So if I'm comparing atoms with different number of protons, the ones that have more protons in the nucleus will attract the electrons more strongly. So the electron to be removed will need higher ionization energy. What about shielding? Well, if there are several energy levels between the nucleus and the outermost electron, we say there is increased shielding, and that means that outermost electron will not be that strongly attracted to the positive nucleus, and it will be easier to remove. So the more shells I have in the middle between the nucleus and the outermost electron, that is called more shielding, and therefore the electron will be more easily removed. So I will need less ionization energy. So let's talk about specific things. So in general, we're going to say that if we're looking at the trend of ionization energies, if I'm going from left to right along a period, ionization energy increases. If I'm going from top to bottom down a group, ionization energy decreases. Now let's explain some things. Now, ionization energy could depend on which subshell we're talking about, or sub-level we're talking about. So if I have S, P, and D, of course the S is nearer to the nucleus, the P is further away, the D is further away. So removing an electron from the D is easier. So the ionization energy to remove electrons from the D will be less than P, and P less than S, or the other way around. If I try to remove from an S compared to removing from a P, the one that is removed from the S will need more energy because it is nearer to the nucleus, more strongly attracted to the nucleus. An electron that is removed from the P and another one removed from the D, then the one removed from the P will need more energy because it is closer to the positive nucleus. What if they are all in the P, but they have different fillings of the P? So we should know that P has the P sublevel has 3 orbitals. Each orbital needs 2 electrons. If all of them are filled, then this P sublevel is stable. it will be very difficult to remove an electron from here. I will need more ionization energy. If I have half filled, this is still relatively stable, so it still needs more energy than something that has paired. Remember that a pair of paired electrons repel each other. So it's easier to remove an electron from a paired p orbital than to remove it from a p3 sublevel in which the half-filled sublevel is stable, and the half-filled sublevel that is stable, if I remove the electron from a filled sublevel, that is more stable and that will need more energy. Okay, so what else? Well, if I have S, for example, sublevel, if the S is filled, we said any sublevel that is filled is stable. And it is more stable than something that is half-filled. And the half-filled is more stable than something that has paired electrons. So if I'm comparing between something, I'm taking an electron from an S2 or taking an electron from an S1, the one from S2 will need more energy because the S2 is stable, it's filled. Okay, so looking at these variations, let us take a look if I am crossing across period 2. What is happening to the first ionization energy in general from left to right? As you can see in the graph, we have first ionization energies of the elements in period 2. What is generally happening is that the ionization energy in general is increasing. And then we say, why is it increasing? Going from lithium to neon, why is the ionization energy increasing? You should remember that when we go across a period from left to right, what is happening is the number of protons in the nucleus is increasing. But we're attracting the same number of shells. So going from left to right, the number of protons is increasing. The atomic radius decreases because the positive nucleus is attracting these same number of energy levels more strongly as we go to the right, and therefore the atomic radius decreases, and therefore the electron we're trying to remove is more strongly attracted to the nucleus, so it will need higher energy. So as we go from left to right in any period, the ionization energy in general increases. But as you can see, there are parts where it decreases again and there are parts where it increases again. So if I'm going from lithium to beryllium, now from lithium to beryllium it's increasing. Now if we say why is it increasing, this is because lithium, the electron I am removing is in the second energy level. I have one electron, I'm going to remove it, so I will need a certain amount of energy. Now, if I go to beryllium, I'm trying to remove the electron from a 2s, and the 2s has 2 electrons, that is stable. So, we said as we go from left to right, the beryllium, for example, has 4 protons attracting the 2 energy levels. Lithium has 3 protons attracting the same number of energy levels, so the atomic radius is decreasing. So with beryllium, the atomic radius decreases because it has more protons attracting the same number of shells. The atomic radius is smaller, so the outermost electron is more strongly attracted to the positive protons in the nucleus. And besides, you're taking the electron in the beryllium from a complete S sublevel, and we said this is more stable than a 2s1, so it requires more energy to be removed. Please note how we explain all of this. Now, okay, going from beryllium to boron. What happened from beryllium to boron? The ionization energy decreases. Now we need to know why. Remember that beryllium ended in a 2s2. So we have 1s2, 2s2. So the electron I'm removing from beryllium, beryllium has 4 electrons. The electron is from 2s2. I'm removing an electron from a 2s sublevel. Now boron it has 5 electrons, so the electron I'm removing is from the 2p. And you should know that the 2p sublevel is higher than the 2s. Higher means further away from the positive nucleus. So the 2p sublevel has higher energy than the 2s. An electron, the 2p, is more easily removed since there is less attraction forces to the positive nucleus. Remember, the electron further away from the nucleus, less attraction forces to the nucleus, and therefore more easily removed. So boron has lower first ionization energy than beryllium. And then going from boron, carbon, nitrogen. What is happening from boron, carbon, nitrogen? Well, it is increasing. Now, why is it increasing? Boron, we have 5 electrons. The electron we're removing is from a 2p that is attracted to 5 protons in the nucleus. Now, carbon has 6 total electrons. The electron we're removing is also from the 2p, but then it is attracted to 6 positive protons in the nucleus. Nitrogen has 7 positive protons in the nucleus. So they're all being removed from the same sublevel, but we have increasing number of protons, and that means the radius is decreasing as we go from boron to carbon to nitrogen, and therefore same sublevel, the number of protons is increasing, so the attraction forces between the outer electron and the positive nucleus increases, the radius is decreasing, and so the electron is more strongly attracted to the nucleus and less easily or more difficult to remove. What about from nitrogen to oxygen? Well, we found that from nitrogen to oxygen, it is decreasing. Now, why is that? So, if we distribute the electrons of nitrogen, you will find that we are removing an electron from a 2p3, and this is half filled. And we said a half-filled sublevel is more stable, difficult to remove the electron from it. But when we look at the electron we're removing from oxygen, it's a paired electron that is already repelled by the other electron, so it is more easily removed. So the ionization energy decreases from nitrogen to oxygen because the half-filled sublevel in nitrogen is more stable. The paired electrons in the 2p of the oxygen repel each other, so less energy is needed to remove the electron from oxygen. Are we following how to explain all of this? Okay. Then we go from oxygen to fluorine to neon. We find that the ionization energy is increasing from oxygen to fluorine to neon. This is because as we go from oxygen, fluorine, neon, we have the same number of energy levels, but the number of protons in the nucleus is increasing. Oxygen has 8 positive protons in the nucleus, fluorine has 9, neon has 10. And that means when we're removing from oxygen, we're removing one of the paired electrons. Now, in the 2p, we have more electrons. In the neon, we have a filled, completely filled, stable sublevel. So increasing the number of protons in the nucleus increases the attraction forces with the outer electron. Of course, also we're going from oxygen to fluorine to neon. The radius is decreasing and the outer electron is more difficult to remove. What about noble gases? You should realize that in each period, the noble gas is the one with the highest ionization energy. So the first ionization energy of noble gases is very high. This is because, of course, you should realize that the noble gases have a completely filled sublevel. So helium, the electron we're removing is from 1s2. In neon, the electron we're removing is from 2p6, 3p6, and so on. So this is a completely filled shell that is very stable and the electron is more difficult to remove, and that is why for each period the highest first ionization energy is in group 0, or the noble gases. What if we're looking at magnesium? If we say that the third ionization energy of magnesium is much greater than the second, well, let's look at magnesium. Magnesium has 2 electrons in its outermost shell. So the first ionization energy is removing one of these two outer electrons to form a +1 ion. The second ionization energy is removing the second electron in that third energy level. Now, when we come and remove or try to remove a third electron, we're trying to remove it from an inner shell that is closer to the nucleus, more strongly attracted to the nucleus, and therefore we will have a huge jump in the ionization energy. So the third ionization energy of magnesium is much greater than the second because it results from breaking up of a completely filled shell, which is stable and therefore will need much more energy. What if we're looking at group 2A? He's saying the ionization energy of group 2A is greater than expected. Well, this is group 2. Beryllium, magnesium, calcium. Group 2, of course, is has the electron in a filled s sublevel. This is a stable sublevel, so very difficult to remove the electron from it. So we'll find that the ionization energies of group 2 are very high. What about group 5? Again, ionization energy of group 5 is greater than expected. What is group 5? Nitrogen, phosphorus, arsenic, antimony. Well, all of them have a half-filled p orbital. So we are removing the electron from a half-filled p sublevel, and that is a stable sublevel that will need a lot of energy to remove the electron. Again, why is it difficult to obtain, for example, sodium 2+? So in order to remove 2 electrons from sodium or a second electron from sodium, this is very difficult. It will need a lot of energy. Or if I remove 3 electrons from magnesium, it needs a lot of energy. 4 electrons from aluminium, this needs a lot of energy. Why is that? We said sodium is something that has the outermost electron in the 3s. So I have 3s1. If I remove it, this is the first ionization energy. So it's okay to get sodium +1. This is easy. But then +1, if I want to remove another electron from this positive ion, I need to remove an electron from a completely filled 2p sublevel. I'm going into an inner shell that is closer to the nucleus, more strongly attracted, so we'll have a huge jump between the first and the second ionization energies. What about magnesium? Well, magnesium has its outermost electrons in the 3s. If I remove one of them, that is my first ionization energy. If I remove the second, that is my second ionization energy. But if I try to get a third ionization energy, I am going into an inner energy level, closer to the nucleus. The electron is more strongly attracted to the nucleus, so this will have a huge jump, or it is difficult to obtain the +3, or actually the ionization energy to get the +3, that is very high. Again, aluminium. Aluminium has 3s2, 3p1. So the first energy, ionization energy, will remove the 3p1. The second ionization energy will remove the 3s, an electron from the 3s, which is relatively close. It's still in the same energy level. The third ionization energy will remove the second electron that's in the 3s. But if I try to have a fourth ionization energy, then I'm trying to remove an electron from an inner complete shell, and this will need much more energy. So I will have a huge jump between the third and the fourth ionization energies. So looking at the periodic table in general, what happens to the first ionization energy if I go from one period to the next? So for example, I have helium and then I want to go to lithium. So what happens from helium to lithium? There is a huge drop in the ionization energy. It decreases. Again, if at the end of that period I remove the electron, the outermost electron from neon, and then I want to remove the outermost electron from sodium, there is a huge drop in ionization energy. Now, why is this happening? Of course, if I'm going down to a new period, that means I'm removing the electron from a further energy level. So there is a sharp decrease in the ionization energy from the end of one period to the beginning of the next, because the electron is going to the next period. The electron I'm removing is one shell further away from the nucleus. So there is what we call shielding. We said there will be more shells between the nucleus and the outermost electron. So that means less attraction force to the positive nucleus. So less energy is needed to remove the electron. Okay, what if we're going down a group? So we're going down lithium, sodium, potassium, rubidium, cesium. Well, ionization energy decreases. Again, why does it decrease? Remember, I'm removing the outermost electron. As I go down the group, the electron is further away from the nucleus. We have more and more shells between the electron and the nucleus. This allows more shielding, so less attraction force to the positive nucleus. So that makes it easier to remove the outer electron, and the energy required to remove the electron will decrease. So in general, you should realize that going from left to right, ionization energy increases. Going from top to bottom in a group, the ionization energy decreases. So let's take a look at some questions. This question says the first ionization energy of sulfur is lower than that of phosphorus, and he wants the best explanation for this. What is sulfur and what is phosphorus? And we're talking about the first ionization energy. Now, sulfur, you look at the periodic table, it has 16 electrons. That means we're going to distribute it so that the electron I'm removing is from a 3p4. What about, and if we distribute, remember the 3p4, we find that that means in the 3p, the outermost 3p sublevel, there is paired electron, and we said the paired electron will repel each other, so it will be easy to remove that paired electron. But for phosphorus, phosphorus has 15 electrons, so we distribute them. We find that the electron I'm trying to remove is from a 3p3. This is a half-filled sublevel, so more stable, less easy to remove. So the ionization energy of phosphorus would be higher. In addition to the fact that, so let us take a look one by one. Which of these is correct? So he's saying the sulfur is lower because atomic radius of sulfur is greater than phosphorus. Well, let's take a look. Where is sulfur and where is phosphorus? We said as we go from left to right in the periodic table, the atomic radius does what? The atomic radius decreases, because we said we have the same number of shells, increasing number of positive protons attracting the same number of shells. So as we go from left to right, the atom becomes smaller. So when he says the atomic radius of sulfur is greater, no, actually, it is not greater. Sulfur would have a smaller atomic radius. So A is wrong. What about B? The electronegativity of sulfur is greater than that of phosphorus. Well, he's asking for what is the best explanation. So when we explain this, we do not use electronegativity. But then when he says the repulsion between the outer electrons of sulfur is greater than that of phosphorus, well, that would be a correct answer, because we said the sulfur has a 3p4, so one of the p orbitals has paired electrons, and these will repel each other, so we will be able to remove it more easily than an electron from a half-filled p sublevel in the phosphorus. And the other choice that we have is the shielding by the inner shell electrons of sulfur is greater than that of phosphorus. What do we mean by shielding? We said shielding is the number of energy levels in the middle. Well, the electron in both cases is from a 3p, so actually it has very similar shielding. It has the same number of energy levels between the positive nucleus and the outermost electrons. Okay, what if he's saying which is a reason why fluorine has a higher first ionization energy than oxygen? Remember, when you answer these questions, the first thing you ask yourself is, well, where is fluorine and where is oxygen? What would be the electron distribution of each? So oxygen, for example, has 8 electrons, so this is how we will distribute it. And that means oxygen has a paired electron in the 2p, which will repel each other, and we can remove it more easily. If I compare it with phosphorus, what about, fluorine? What about fluorine? We have an electron that is being removed from a 2p again, and it is paired again. So the difference between oxygen and fluorine would be what? It would not be fewer unpaired electrons or fewer shells, but it will be the fact that as we go from oxygen to phosphorus, oxygen has 8 protons, positive protons in the nucleus attracting the electrons. Fluorine has 9 positive protons. So we said as we go from oxygen to fluorine, the atomic radius is smaller. So that means the electron, the fluorine, is more strongly attracted to the nucleus. Why? Because fluorine has more protons attracting the same number of energy levels. Okay? Explain why the first ionization energy of nitrogen is greater than the first ionization energy of phosphorus. Where is nitrogen and where is phosphorus? Well, nitrogen has 7 electrons. So what we're trying to remove is an electron from a half-filled 2p orbit. What about phosphorus? We're comparing it with phosphorus. Well, phosphorus has 15 electrons, and that means 15 protons also. So why would be, and the electron, notice that the electron we're removing from phosphorus is from a 3p. That means a third energy level, while the electron we're removing from nitrogen is from a second energy level. So if we're comparing nitrogen to phosphorus, of course, this is because the electron we're removing from the nitrogen is from a lower energy level, less shielding, more attraction forces between the electron and the positive nucleus. So this needs more energy to be removed. Are we following? Okay. This question says we're talking about arsenic to rubidium, and they have atomic numbers 33 to 37. And he's giving me the first ionization energy of these elements. Write the equation with state symbols which represents the first ionization energy of arsenic. Now, if he tells me to do that, we said, what is first ionization energy? It's the energy needed to remove an electron from what? From gaseous atoms to form gaseous +1 ions. So this is how we represent it, and don't forget the state symbols. They have to be in the gaseous state. Explain why the first ionization energy of selenium is lower than that of arsenic. Where is selenium and where is arsenic? Well, in selenium, the atomic number is 34, so the electron I'm removing is from a 4p4. The electron from arsenic is a 4p3. So if you're comparing these, the selenium will be lower. Why? We said that is because the arsenic is half filled. For the arsenic, it is 4p3. So I'm trying to remove an electron from a half filled level, and that is stable, needs more energy. But selenium, I'm trying to remove the electron from a paired orbital, an electron that has paired electrons, and we said the paired electrons repel each other, and the electron would be easier to remove in selenium. Explain why the first ionization energy of krypton is higher than that of selenium. Well, again, we look at the ionization energy for krypton. Krypton has a filled P6, 4p6. So krypton has higher number of protons, same number of shells, atomic radius smaller, electron is nearer to the nucleus, more difficult to remove, and it is a completely filled sublevel which is stable and difficult to remove. Explain why the first ionization energy of rubidium is lower than that of krypton. Well, let's see. What is rubidium? The electron rubidium is in a higher energy level, further away from the nucleus, more shielding, less energy is needed to remove the electron. Do we understand how to explain all of this? Now, he's given me the first ionization energy for sodium is this, and for magnesium is this. Suggest a value for the first ionization energy of aluminium. We said going from sodium to magnesium, it increases. Now, going to aluminium, you would expect it to be, we said the electron in the magnesium is removed from an S2. Now, going into aluminium, we are going to remove an electron from a p orbital which has higher energy. So I would give it less than the magnesium, somewhere between sodium and magnesium. Why? Because the 3p electron in the aluminium is higher energy level than the 3s, so less attraction to the nucleus, less energy is needed to remove the electron than for magnesium. The chart below shows the successive ionization energies of potassium. So he has first, second, third, and so on of potassium. He's saying estimate the first ionization energy and the 19th ionization energy of potassium. Well, notice that the y-axis has log of ionization energy. So if we look at the graph for the first ionization energy, it is about 2.6. But then that means, so the log of the ionization energy is 2.6. So how do I get the ionization energy? Is 10 to the power of that. So 10 to the power of 2.6, so that is the number. What about he wants the 19th? Where is the 19th? It's about 5.7. But that is the log of the ionization energy. So the ionization energy itself will be 10 to the power of that, and that comes out in to have this number. Explain why the log of the ionization energy is used instead of the ionization energy. Why didn't he just plot the ionization energy on the y-axis? Of course, that is because the ionization energies are very large numbers and very difficult to put on a graph, so we use the log of them, of these numbers, in order to be able to fit it on the graph. Explain why there is a general rise in the value of the successive ionization energies. So remember, these are the ionization energies for potassium. So first, second, third, until the 19th ionization energy. As we remove electrons, the ion is smaller, the electron to be removed is nearer to the nucleus, so there is stronger electrostatic attraction forces between the electron and the positive nucleus, and that needs more energy to be removed. And this applies to any atom that we're talking about. as we go from first to second to third ionization energies and so on, these are higher and higher value. So how do we predict the group of an element from a given set of data for successive ionization energies? Well, we already mentioned, if I'm talking about group 1, the first ionization energy is a certain amount. But once I go into the second ionization energy, then I'm going into an inner shell that is closer to the nucleus. So there is a huge jump from the first ionization energy to the second ionization energy. Then I know that this element was in group 1. Now, if the element was in group 2, well, the first ionization energy is a certain number because I'm removing the first electron in the outermost shell. Group 2 means it has 2 electrons in its outermost shell. The first ionization energy will remove the first electron. Well, that's a certain amount. The second ionization energy will be slightly higher because we said as we go successive, then it is more and more ionization energy. But after the second ionization energy, if I try to remove a third electron, we said that means I'm going into a shell that is nearer to the nucleus, which is complete and stable, more strongly attracted to the nucleus, so there will be a huge jump in the third ionization energy, and so on. If we're talking about something in group 3, then removing the first electron is fine, removing the second electron, well, slightly higher, removing the third electron slightly higher, and then if I try to remove the fourth electron, I'm removing it from an inner complete shell that will have a much higher ionization energy. So if we look at this question, he says the first 6 ionization energies of some sort of element is this. And he's asking me which group in the periodic table is this element. Well, let's see. The first ionization energy is 1086. The second ionization energy is 2300 and something. So that's a difference of about 1000 and something. From the second to the third is a difference of about 2000. From the third to the fourth, it's a difference of about 1600. But going from the fourth to the fifth, the fourth ionization energy was 6000 and something. The fifth ionization energy is 37,000. A difference of about 31 or 32,000, that's a huge jump. That tells me that my element was in group 4. Do we understand that? The first huge jump indicates we're going from the outer shell into an inner shell. So the number of electrons in the outer shell, that is the number of ionization energies before the huge jump. Okay, so that's the end of this. It was about ionization energy. I hope this was okay with you, and please keep listening to the videos, and thank you.